Yeah, but I won't talk about Artemis features in detail. It's just this is one application of Artemis. And I do have a question for adaptive mesh refinement because we don't have that yet. Okay, so this talk is in collaboration with the data science group at Berkeley Lab and also a quantum expert from Tokyo University. It's HPC-driven modeling with ML-based surrogates for Magnon-Photon dynamics in hybrid quantum system. So we also have microelectronics application. We also have AMReX-based numerical simulation, and we also have some machine learning. But the problem and the numerical module and also the machine learning method is completely different from the previous talk. So let me walk you through this problem. So when I was designing the slides, I didn't realize that the previous talk is right before this one. So for this slide, I give some background of the application. So like I mentioned previously, like 20 minutes ago, there's a growing demand for electronic devices for energy and cost efficiency, right? So what kind of device am I talking about? For example, the autonomous cars, smartphones that everyone is using now, and then quantum computers, transistors is getting smaller and smaller. The current state of the art, I think, is the 2 nanometer node, and people cannot really get it lower. So people are reaching to the limit. That's why they start looking for other technologies and materials beyond semiconductor. And then acoustic filters that really connect electromagnetic dynamics and acoustic dynamics together. So there are a lot of devices and needs here, but really the general trend is just miniaturization and integration. We need more advanced functionality in smaller and more compact devices and systems. So this is motivating us to search for novel materials and new technologies. And we always use numerical tools to design electronics. That has been the practice for the past decades. For example, when we're talking about IC design, we're using cadence or ADS. And when we're talking about physics design, we have simulation tools all the way from HFSS to COMSOL. That is I think, one of the best multi-physics simulators in the market that's available. But that's only because people don't have better choice. I think if everyone knows how to code and how to do numerical simulation, they wouldn't go to COMSOL. That's why we came into this field and try to solve this problem and provide reliable design tools for people. And micromagnetic simulators like OOMF and MPI+X, but they have demonstrated problem of scalability and coupling and transparency of the physics, right? So the challenges are pretty clear. The efficiency of the simulation is pretty low with existing softwares. And then we don't have automated design and optimization. Basically, we don't have a out of the outer loop process designed properly to do inverse design. So let me give you an overview of what kind of physics we care within the microelectronics subteam of CCSE group. Whenever we're talking about electronics, devices, and materials, electrodynamics or electrostatics is always the #1 concern. That is Maxwell's equations and some derivative of Maxwell's equations, for example, Poisson equation for electrostatics and Poisson equation for magnetostatics, right? So we're talking about this PDEs for this piece of physics. And then charge movement, of course, in semiconductors, in metals, and in insulators, charge movement is always the #1 concern. And they, of course, talk to your electric signal through materials such as ferroelectric material, piezoelectric material, and other type of materials, right? The recent technology is pushing us toward new devices and physics. For example, spin waves that is existing in magnetic materials. So we're just talking about magnets and spintronic simulations. But spin waves can also couple to electrodynamics and electrostatics. In magnets, I was just talking about, we're talking about electrostatics. We didn't care about the dynamic effect from Maxwell's equation, but that's not the complete picture. For high-frequency applications, electrodynamics with the full Maxwell solution is needed for spintronic application. And these two talk to each other through ferromagnetic or anti-ferromagnetic material. Of course, spin wave and charge also talk to each other because spin is the property of electron. If electron happen to move or electron happen to talk to other materials, then spin wave and charge movements start to entangle, and there's this type of material called magnetoelectric or multiferroic, that's what I was talking about, comes into play. And you might ask, would all of the physics start talking to each other so that it gets so messy and beyond our capability? Yes, that has been the case for multiferroic materials and many complicated systems. So to solve this problem, I guess I didn't have to overemphasize the need for multi-physics simulation, right? But now really the challenge here is we're really dealing with very different spatial and temporal scale. Here we have the time and space diagram. If we draw a line here that indicate the velocity of EM wave, right? So the slope would be the speed of light if we have electromagnetic wave here. And then acoustic wave is much slower, and that gives us a smaller wavelength, but a longer time duration. And then if we're talking about spin wave in magnetic material, that has the similar wave velocity compared to mechanical wave, but much, much smaller in spatial scale. The wavelength of spin wave is probably on the order of tens to hundreds of nanometer instead of microns. So if we are just simulating one single type of material, then that's easy. We just need to make sure that we cover a short range of time and a narrow range of space, right? If we're only interested in one type of the phenomena here. But what we're dealing with is a very complicated multi-physics, multi-scale problem. That means that we need to our simulation has to span over a wide temporal range and a very large spatial range. So that brings in a really challenging situation. So with Artemis, thanks for bringing that up, we are able to solve the Maxwell's equation very efficiently. By the way, Artemis is built on top of WarpX, so we take advantage of all the good features coming from WarpX, including GPU parallelization and all the pipelines. So what's built on top of WarpX is this spintronic module within Artemis. Here, the lower part here where you see this yellow patch, this is an electronic circuit that we call coplanar waveguide. It's a CPW resonator. Basically, what it does is you see these two shoulder patches here, which are wider than the others. These are the ground patch. I'm connecting these two patches to the ground to make sure that there's no field or no voltage applied on these two ground patches. What really matters are the center parts here, the three yellow patches. The center patch, you can see that it's disconnected from the other two, right? That means that this is an isolated resonator. So if I feed in an electric field, the electric field will be bounced back and forth within the center resonator. So it does not, the majority of the electric field will be trapped within this resonator. And then the constructive interference between the original and the reflected field will form a resonance. So this is what we call photon. Just for information, my own understanding of photon and resonance is they're the same thing. Photon is basically a more fancy and quantum way of calling a standing wave. So if I have electromagnetic waves confined within a space or a structure, and then a standing wave forms, which means that we have a discrete energy landscape, right? The bandwidth is discrete, and we have some energy band gap. that means that we have photon, which is more quantized way of calling a standing wave. Okay, so same terminology applies for magnon. Magnon is also a quantized way of spin wave. Here I have this red patch here. The material is cobalt iron. I have the spins, which represent the ferromagnetic resonance. So the spin would resonate in this red patch here. And this resonance gives us a discrete energy band gap, which we call magnon. Because magnon structure and photon structure are right next to each other, the magnon and photon will start exchanging energy between these two. And this is what we call Magnon-Photon hybrid coupling. This is the simulation result. So this is a top view of the field. You can see two stripes here, which are in blue and brown. These are green and brown colors at the two shoulders. These are our electric field. And in the center, you can see one single stripe that is overlapping the location of the red stripe, which is our magnetic material, right? So the center stripe in red and blue, this is our magnon. This is our magnetization. It might be a lot of information in this animation, but what I want to emphasize here is the interchange between these two states. When we have maximum magnetization in the center stripe, the electric field at the side would be minimum. So I'll show the animation one more time. So at the function of time, when the center stripe is the brightest color, the side stripes are zero. There's no electric field. And vice versa. When the side stripes are the brightest, the center stripe is zero, right? It doesn't have any color. So that means that we're clearly seeing the energy being interchanged between these two states. And this phenomena will be more obvious if we look at this plot. The black curve is EX, and it's our electric field, and the red curve is our magnetization field. When we're having a peak of E, we're having a null of M, and vice versa. So this is energy exchange. Okay, let me come back to this one. Yeah, so with Artemis, we're able to simulate both Maxwell's equations and LRG equations interchangeably in a simultaneous way, and we're able to solve both E and M at the function of time together, right? So this is our simulation result. And then, so like I mentioned, this is still a very severe multi-scale problem, and we're still having problem with the simulation time. So this is just so much we can do with the powerful AMReX GPU scalability, but because we're dealing with a four order of magnitude scale difference, so the simulation is still slow. It's taking like 48 hours for one single run. That motivates us to search for machine learning surrogates. Basically, if we just simulate with Artemis for a shorter amount of time, and then if the machine learning surrogate can predict the future time step for us, then we can save the time of the very costly numerical simulation, right? So this is the framework of the machine learning surrogates. The neural network technology we're using is called Long Expressive Memory. This is built by one of our collaborators from UC Berkeley. It's basically it's similar to LSTM but different. So the gating comes from the PDE information itself. That's the only difference. But other than that, LEM is just a technique for future time series forecasting. So I was talking about the energy exchange on this page. If we do FFT and we show a spectrum here, we can see a very clear anti-crossing spectrum that is indicating a Rabi oscillation like quantum behavior, right? So there's coherent coupling between magnon and photon. So we're able to see that from simulation. Actually, this is, to the best of my knowledge, this is the first time that people are able to simulate this system using numerical modeling. People are not able to do that because of the multi-scale problem. And this is the extracted circuit performance. And one benefit from simulation is we can do crazy experiment. So here is, I did a very crazy thing. I just increased the input electric field intensity to extremely high. I think the field intensity I was using is probably higher than the world-class cyclotron. But then I was able to see something that people are not able to see in real life. So this is what we see in the linear regime, where your electric field intensity is reasonable. But then if I increase it, eventually it kills all the magnetization. We do not have any magnons left. So yeah, I just see this as fascinating. This is what we can do, but other people cannot. And then some machine learning benchmark, we compare the extracted resonant frequency and quality factor from machine learning and compare it to pure numerical Artemis simulation, and we see pretty good match here. We're trying to do spatial temporal prediction. So all the previous simulation that all the previous machine learning results are on single spatial location. But then we would like to generalize it to more spatial locations and see how well that performed. It does not perform well. I have to admit that. This is the relative error of resonant frequencies. And you can see we see quite significant discrepancy between our machine learning predicted and the numerical. So that means that if we pick some spatial location, train it, and then infer at other spatial locations, it still does not give us good result. So this is something we're working on, whether we can come up with better spatial temporal machine learning model so that we can do not only single point time series forecasting, but also spatial temporal forecasting. And this is our scaling performance. I was trying to show this to the machine learning community, and they're very pleased by this. But we know that for the machine learning scaling, there's some trick we can play to make it good. So I won't oversell this. But I think the bottom line is Artemis scalability, thanks to AMReX and WarpX, is almost perfect. Yeah, so with that, I would like to thank all my collaborators and welcome questions.